Thank you. It's a pleasure to be here. So yeah, as you can see from the title, this talk is going to be about state that evolves monotonically and how we can use it in verification and programming. The paper is both about sort of theoretical foundations and an application side. In the talk, I'm going to concentrate mostly on the application side through various examples and invite you to read the paper if you want to see the meta theory and correctness results. So in general, what we claim in the paper is this following two things: that monotonicity is really useful, and we can capture its essence in a very neat and clean way. And sort of as a side remark here, so compared to the previous talk and probably also the next talk, we decided not to use a super powerful logic like Inria's for our development, but rather we start with a very simple Hoare logic and then extend it to account for monotonicity, but in a as principled way as possible, and to make the extension as small and clean as possible. So the way I'm going to try to demonstrate and back up these two claims is in the following way. I'll start with some very kind of motivating examples. Then I'll show kind of the key ideas behind what we propose as a framework. I'll show how we accommodate it in the F-star language, but that is to say that this applies to other Hoare-style logic as well. So it's nothing really F-star specific. And then I'll show you some other examples. If you want to see more examples and meta theory and correctness results, then yeah, please see the paper. Okay, so let's start with a couple of very basic motivating examples. So consider this small program that's operating on some set valued state. And what it does is that it inserts a specific value v into the state, then runs some complex procedure, and then in the end tries to assert the fact that v is still in the heap, or still in the state. So the way that you would usually prove it is by proving a stateful invariant or a Hoare triple about this complex procedure in the middle, that if we start in a state that v is in the state, that if we start in a state which contains v, then we finish in a state that also contains v. This has a couple of downsides. So usually you have to thread this invariant through the whole proof of this complex procedure. Moreover, this doesn't guarantee that the v might have been erased temporarily and then having put back afterwards. And this is kind of crucial if you're doing security proofs. You want to guarantee some properties about your logs that they only increase monotonically, for example. And it's also this sort of carrying the invariant through is very sensitive with respect to trying to add, say, another w into the state and doing similar thing that I want. In the end, I want to assert that the w is in the state. So you might have to go and revisit the proof of complex procedure. On the other hand, if we were to know that this complex procedure never removes any elements, so it only does reading and inserting, then this invariant that we're talking about is really invariant. So it's stable with respect to any possible state updates that the complex procedure can do. And in that case, we would like our logic to give this as the final assertion here, essentially for free. We would like to have enough power in the logic to get it for free, and this is mostly about what I'm going to tell you about in this talk, is how to extend Hoare logic with this sort of capabilities to do it. So this is sort of monotonicity in verification. It's a very toy example, but it kind of illustrates the trade-offs that you have. But also monotonicity plays a key role in programming, and even if you don't realize it yourself. So for example, consider ML and the type of references. You can think of a value of type FA as essentially a proof of existence, that a value of type A exists in the heap. So why this is correct is the correctness really crucially relies on monotonicity. And the idea being that the writes that you do never change the type of a reference, and there is no explicit deallocation. So it is correct to have the following in ML, that whenever you have a reference, then it's guaranteed to point to a value of the corresponding type. So in many languages, this is taken as a primitive in your memory model. Instead, here we'll show how a general notion of monotonicity can be used to derive these sorts of ML-style type references in a very nice way. Okay, and as I said, yeah, monotonicity is really useful. So in this talk, you'll see, I'll come back to these examples afterwards, and I'll also show you how untyped references and the notion of monotonic references fits in the similar memory model that we use for the type references. But in addition, if you go in and look at the paper, then there are various other examples. So it's possible to temporarily violate monotonicity constraints. You can find two fairly substantial case studies written up in F star. One is about secure file transfer, the other one is about state continuity. And then there are also various pointers to other works in F star that rely on the kind of monotonicity that you see, including quite sophisticated region-based memory models used in the crypto and TLS verification that's done as part of this project Everest. Okay, so let's go on to the next point, which is essentially, I'm going to tell you about the key points about the framework that we're proposing for monotonicity. So to begin with, we focus on monotonic programs and so-called stable predicates. So what does that mean? So in our setting, for each kind of verification task or programming task that you're interested in, we'll fix some preorder. So this might be set inclusion, heap inclusion, and so on. So this is going to govern how our state is allowed to evolve. Then the programs that we are interested in are what we call monotonic programs. So the idea being that whichever way they can mutate the state, these mutations have to respect the preorder that we have fixed. And then the predicates that we are most interested in are so-called stable predicates, which are preserved by the preorder. But to add to this, it's also crucial that we have access to precise predicates that are not stable. And you'll see that in a few slides' time of the combination of the two actually allows us to do, say, the references, for example. And the solution that we provide here, written in English at that very high level, is to extend a simple Hoare-style logic with a means, first of all, to witness that a stable predicate is true at some particular program state. Then a means for turning essentially that knowledge into a state-independent proposition so that it can flow through your pre and post conditions. And then a means to recall this validity of this predicate P in some future state. And what makes it kind of all work is this state independence that allows this knowledge to flow through the pre and post conditions. And then what we do is essentially provides unifying account of various forms of ad hoc monotonicity that was already used in F star. So let's look at how we do it on the example of F star, but you'll see that it clearly you can easily use it to extend other Hoare logics as well. So in F star, you reason about stateful programs using computational type of this form, which is kind of a monadic type, but in addition to being indexed by the type of return values, it's also indexed by a pre and post condition. And thing to note here is the post conditions that we consider are two-state ones. So it's a predicate both on the initial states and the final states. And the other idea is that this is just a pre-post condition refinement of your usual state monad that you know from Haskell. It comes with two actions, get and put, the usual global state actions. Both of them have just trivial preconditions, and the post conditions are what you would expect. So get really gives you the state that's the current state, and it doesn't change the state. And put makes the final state to be equal to the state that you passed it. So this is sort of recapping of how you deal with ordinary state. So now moving on to monadic state, then we are going to use a computational monadic type of this form, which is still indexed by pre and post conditions, but underneath it's also indexed by a preorder that will govern how our state can evolve. Its get action, or I should say the pre and post conditions are typed as they were before. Its get action is also typed as before, but for the put action, we have this extra precondition which requires the state that you want to update, well, the value that you want to update the state with has to be related to the current one. So this is what kind of guarantees the monotonicity and that all our stateful programs adhere to the preorder. So implicitly, we are working, implicitly underneath you have this update monad. And So yeah, so what you had in the previous slide is sort of you have get and put operations, but we still need something more. And as I said, there will be 3 ingredients that we'll add to this to be able to do the kind of reasoning that we had in the beginning. And this brings us also back to the title of the talk. So as the first ingredient, we add this, we call it in the paper logical capability, but you can also think of it as a modality. And in some ongoing work, we're actually taking the modality aspect more seriously. So we have this logical capability called witnessed, which takes a predicate and states and gives you back a proposition. The idea being that witnessed P holds if the P was true at some past state and is stable, so it will hold everywhere in the future. Or alternatively, if P is true now and holds everywhere in the future, together with just a weakening principle. Yeah, and in addition, we add to this picture a kind of an introduction rule and an elimination rule for this witness, but we can't do it directly in the logic of pre and post conditions, but we have to add these stateful operations. So we have 2 operations, witness and recall. The first one is, think of it as an introduction rule, so it takes a predicate, and if it holds now and if it's stable, it gives us this knowledge that witnessed P is true. And recall, if we know that we have witnessed P at some point, then P will be true now. So that was a kind of a very quick sketch of how we add it to F star, and let's go back to the examples that we already saw and discussed and see how we can do it in this framework. So first of all, this motivating example about inserting values into a set-valued state. So what we do here is we pick set inclusion to be this preorder that we program with. And in addition, we prove that this complex procedure can be type checked against this type MST with the preorder picked to be this inclusion. And then in order to prove this assertion in the end, what we only have to do is insert a witness and recall at appropriate places. So here, witness gives us gives us knowledge that the V is in the state at this point, and as it's state independent, it can flow through the pre and post conditions. Once at the right place, we call a recall to know that V is indeed still in the state. And if you want to add in another W, then this is handled similarly. You just insert the witness and recall operations at the right places. So you don't have to go and then revisit the proof of CP to prove that. And if you could also consider monotonic counters by picking natural numbers and the usual greater than equal order, and inserting witnesses and recalls at the right places. You can easily also reason about monotonic counters, and that the values that if you saw that the value was I at some past state, then in the future is still at least I. So now these ML-style typed references. So what we have to do is we have to say what is the state that we instantiate the MST with, and what's the preorder. So for state, we just define essentially the expected model of a heap. So it's just a mapping from natural numbers to memory cells paired together with a counter that just gives us the next fresh reference. And memory cells are either unused or used, in which case they contain a type and the value of that type. And then the preorder is just heap inclusion written out in a pattern matching style. And crucially, when we are relating to used memory cells, then we don't allow strong updates. So the types have to be equal. And using that, we can define a new computational type or effect, ML-ST for ML state-like thing, which is just going to be defined on top of MST with the state assigned to heap, the state picked as heap and the preorder picked as the heap inclusion. So the next, based on that, we have to say, so what are the references? And here, monotonicity comes in as a crucial element. So the idea here is that we define references as a refinement of natural numbers, but the refinement is exactly that at some point in the past we have witnessed that the reference is in the heap. And because our preorder is heap inclusion, then we know that everywhere in the future, whenever we get a value of ref A, it's sound to recall that the reference is actually in the heap. And yeah, as I said, so the crucial thing is that this containment predicate is stable with respect to this heap inclusion preorder. And as a last step, we also have to define the operations of this ML-ST effect, namely allocating a reference, reading from a reference, and writing a new value to the reference. And the way that we do it is we just use the underlying actions of this global state this global state MST. So we just has get and put operations. So the idea is that with the get and put operations, we read the heap, we do some manipulations, and put the heap back, as I'm showing here. But then crucially, if you take the allocation operation, then as a very last step, we call this witness operation of MST that provides us the required knowledge that the reference is in the heap in the current point. And in the case of the read and write operations, before reading the heap and doing anything with it, we call recall, which allows us, which enables us to recall that the reference is actually in the heap and do the select and update operations that one needs to do. And then, as I said, one can extend and enrich this memory model further. So first with untyped references that you might see in, say, like in Hoare-type theory, in which case, the type of the reference doesn't say anything about what type of values you have, sort of polymorphic in that sense. The types of the operations that you consider are much weaker, so you don't get any strong guarantees. The way that you can do it is essentially the use cells will be just tagged with am I typed or am I untyped. And you can also further extend it to support the allocation if you want. And then you can also consider a variant of type references that we call monotonic references, where each reference gets a preorder, and this gives you much more flexibility that you don't need to define a whole new heap model for any for your specific problems, but you can actually just use different references for specific programming or verification problems. And this amounts to just storing also the preorder at each of the memory locations. So that was a very quick overview of what we did in this paper. The takeaway that I would like you to go away from here is that this sort of monotonicity can be distilled into a very simple and general framework. And in addition, it's very useful both for programming. So you saw that we could implement typed references, untyped references, monotonic references, but also for verification. So a lot of the work that's going on in the Project Everest on verifying crypto algorithms and verifying the TLS protocol is crucially relies on this notion of monotonicity. And you can see the paper for more examples. A meta theory that's based on a form of instrumented semantics where we keep track of the predicates that we have witnessed, and then some first steps also towards monadic verification for this MST effect. And at this point, I would like to thank you, but also mention this part here, that the F-star team is always actively looking for clever interns. So if either you or any of your students are interested, then get in touch. And there are a lot of cool things happening there. So thank you.
Okay, so as before, the first question will come from the internet. So the first question is, these witnesses seem related to the persistent propositions Derek Breyer mentioned in his keynote. Do you see a formal
Yes, the formal connection is there, slightly more informally. So if you go back to the original PCM-based logics from Lars and his coworkers, so an example that they consider there is monotonic counters, and you can express it using a freely duplicable predicate. And the idea, is that once I have this, I know that the counter is at least I. And this you can propagate through your pre and post conditions because it's freely duplicable and you can do whatever. In our case, when we were defining these references, we were also crucially interested in having access to precise predicates. So as far as we can see, if we were to do it, say, in Iris, then the encodings would get quite sophisticated, and in many ways we wanted to avoid that and be sort of in a domain-specific setting as possible. And also, so the style that we're using here that scales very well because we can do very easy SMT-based automation. So that's crucial for the kind of verification tasks that are ongoing in Project Everest.
So yeah, okay, a follow-on question to that is, so, I mean, in Iris, we can certainly reason about precise counter values, as in my talk, right? I showed two predicates, the current counter value and the lower bounds. So I don't exactly understand I don't exactly understand the second bullet on the slide.
Okay, well, perhaps we can take it offline.
Yeah, we can certainly take that offline. I guess the other question is, I'm curious about what is actually enabling the scaling well? I could certainly believe that by looking at by working with a more restrictive notion of monotonicity, you can scale well to SMT. But I'm just curious, what exactly is the thing that helps you?
So the thing that helps here is that the pre and post condition logic that we consider with this witnessed capability or modality is kind of a very simple modal logic. So you don't have any, from the SMT viewpoint, you don't have any complications of sort of separation logic and separation around. So it's really first order predicate logic, classical logic with an extra modality that you can easily axiomatize for the SMT. So
okay.
That's sort of at a very high level, that's the idea, what makes it scale, at least from the SMT perspective. Very well.
Okay, and one quick follow-on question. So you showed these different examples that use different transition or different preorders.
Yes.
Do these somehow compose?
So in this work, we didn't consider composition yet, but
okay.
it's definitely one of the low-hanging fruits to consider perhaps a graded monad style indexing with the preorders where you can compose them and combine them in a kind of compositional way.
Okay.
Do we have any other questions?
Okay, do you think someday you'll be able to free a reference?
Say again?
Free a reference.
So what we can do here is we support deallocating the reference for the untyped references. So that was sort of an extension of the memory model that I considered. For the typed references, in the memory models that we consider, we don't have deallocation.
Sorry. What was the preorder then for the one where you free?
So the preorder, we can take it offline. The idea there is we can take it offline. It's a very long decision.
Could you use this technology somehow to prove in a semantic way type soundness of an ML-like language? So in Iris, we can use the co-state and invariants and so on to construct a logical relation of an ML-like language and use that to semantically prove type safety. Could you do that using this technology as well?
It's a very good question. I haven't thought about it, and from the top of my head, I won't make any claims. So.
Okay, good, thank you.
We have time for one more question if anyone wants to ask one. No, then let's all